All right, so the title of today's lesson would be 1.2 Walking Rates in Linear Relationships. And we're just going to get into one specific part, this letter C. Four other friends who are part of the walkathon made the following representations of their data. So you can see that two look like tables and the other two look like equations. First of all, you need to understand that relationships are represented by straight lines on a graph called a linear relationship. So it's straight line, linear. And that relationship between the independent and dependent variable have to be linear, okay? So there are a couple things for you to keep in mind when looking at a linear function. An example, that bicycle rental cost, you can see that as the number of bikes increase, the total cost in dollars increases as well, going up in a certain ratio. So to do that, we're going to look at each individual one: George, Elizabeth, Billy, and Bob. So I introduced this concept of slope-intercept form in the last video. The formula is y equals mx plus b. So if we were to break this down, the y is the dependent variable and the x is the independent variable. So you could see right here that the input, so if you have an input-output table or a table, you would have the input over here and the output over here. So what you put in, you get out. So input is x and output is y. The key to that is the independent variable to the x-axis on the graph, okay? So this is the independent, the x-axis, and this is the y, the the dependent variable. So you have your input-output, and so that's x in that equation, and y. The m and the b are specific. M is the slope, or the rise over the run, or what we've been working with lately, the rate. So the rate is what we've been using, our walking rate, okay? The last part is b, and the easiest way to remember b is where you begin, hence the letter B that starts begin. So where are you beginning? Are you beginning at 0? Are you beginning at 5, at 10? Wherever you begin is very important. So that's what the B is representing. The other thing that it's representing, or the other way you could look at that, is where you cross the y-axis. That's called the y-intercept, where you intercept the y-axis. So wherever that may be on the line, okay, would be B. All right. So let's take a look at each individual. George's walking rates. The first thing you need to know is that there a constant rate of change? If there is, it's linear. So we look at the time in seconds. You can see it's going up 1 second, okay? This is important to look at. Sometimes they're going to trick you here, and they're going to give you, different intervals. So here it's going up by 1, and then you could see the interval. It's going up 2, 7, 2, 9, 5. That is inconsistent. It is not a consistent rate of change. So therefore, George's walking rates are non-linear. Okay, if we look at Elizabeth, you could see that in the x column here, the independent variable, you see they're counting by 2s. And then over here, they're counting by 3s. So in reality, okay, this is linear. So yes, it is linear because the rate of change is 3 meters every 2 seconds. So you could see that because it's every 2 seconds, then you have a linear rate of change. In reality, though, every second is 1.5 meters. So if we were to break this down to a unit rate, you would say that for every 1 meter, okay, 1 second, you're going 1.5 meters. 2 seconds is 3. 3 seconds, 4.5. They don't have it broken down this way, so you have to be aware that sometimes they're breaking it down every 2 seconds, 4 seconds, 5 seconds, and you have to find that unit rate. Every 1.5, it's going up, so yes, it is linear. All right, in this particular problem, Billy's walking rate is represented in equation form. So you learn the equation D equals RT. R is right here at 2.25 for every t second or minute, whatever. So we know that he's going 2.25. We're not quite sure, is it per second, per minute? We're going to assume it's per second. So that is linear because the rate is the same. It's constant. Anytime you multiply it, you're going to be multiplying it by 2.25. That does not change. That is constant. and therefore it is linear, okay? Is Bob. Bob has a walking rate, and his is different. You can see his distance is represented right here. We don't know his time, and the key component is rate. You need to know the rate. You need to know whether it's constant, so we are unsure here of whether or not this is linear. If I know his rate is constant, then I know it's linear. But because I don't know, I can't answer the question. So therefore, I am unsure.